All right, folks. We're going to discuss a method for finding the greatest common divisor of two numbers a little more efficiently than finding the prime factorization of the two numbers and comparing the number of primes, which we'll talk about a little bit later on as well. But this is called the Euclidean algorithm. And it's basically this following fact. We'll do an example of it after we prove this. But this is, let's say, Theorem 39.1, if you like. And it says that, well, if you can write a number in terms of the quotient remainder theorem, so you do a divided by b, and you get that a equals so many multiples of b plus a remainder, then the GCD of AB can be reduced to a smaller problem, which is the GCD of b and your remainder. So let's prove that. So let's consider the following. Let's consider the GCD, we'll call it D, I guess, will be the GCD of A and B. And we know so D is a divisor of A, or a factor of A, since it is the greatest common divisor. And we know that A can be written as QB plus R, like above. Well, A equals QB plus R. What else do we know? Well, we also know that D is a factor of B. So let's rearrange. So we rearrange the above. We get that A minus QB equals R. And since I don't need to write that, I guess, because I already wrote it above. So I have that D is a factor of A. D is a factor of B, so D is a factor of Q times B. So D is a factor of both of these terms, so it's a factor of the entire left-hand side. So D is a factor of A minus QB, and thus, well, A minus QB equals R, so D is also a factor of R. And similarly to the argument that we did in the last video, I think it was Theorem 38.1, we know D has to be the greatest common divisor of B and R. So not only is it a divisor of R, it's a divisor of R, so it's a divisor of B, it also has to be the greatest common divisor. So you can do something very similar like we did in the other proof in Theorem 38.1. Pretend there's another divisor and show that D is always bigger than it. Okay. So that's cool. So we have that proof done. So let's do another quick theorem. So this will be Theorem 39.2, and it states the following. For any natural number A, the greatest common divisor of A and 0 is, of course, A. And the proof, I guess, is pretty simple. I'll just kind of do it quickly. So since all, let's say, B and the integers are such that B is a factor of 0. 0 times B equals 0, well, and of course a is a factor of itself, nothing larger than a is a factor of a, well, we know that the greatest common divisor of a and 0 has to be a. A is definitely a factor of a. A is also a factor of 0. Everything's a factor of 0. And since a is the largest, it's going to be the greatest common divisor. So now, let's talk about the actual Euclidean algorithm. So I'll write it down. I'll write it down in kind of some steps that are basic. So the Euclidean algorithm basically it is as follows. So we want to repeatedly use Theorem 39.1 until we can use Theorem 39.2. That's basically it. And something to think about, and I'll leave this as an exercise for you guys, why are we guaranteed to be able to use Theorem 39.2? Why do we always get it so that one of the remainders is 0? Why is that going to be the case? So let's go ahead and do a couple of examples of this. So let's find the greatest common divisor of 816 and 2,260. Okay, so I'll leave a little bit of the long division for you guys, but we're just doing some long division. So I can write 2260 as two groups of 816, 816 with a remainder of 628. So now, what I'm going to do is going to use that Theorem 39.1. I know the greatest common divisor of 2260 and 816 is the same as the greatest common divisor of 816 and 628. So let's use Theorem 38.1. So let's keep going. So we get that 816, well, it's one copy of 628 with a remainder of 188. And we keep going. Basically what we're doing is our divisor becomes our new dividend, and our remainder becomes our new divisor. So we just keep going like that. The divisor becomes the new dividend, so that is 628. And 188, our remainder, becomes our new divisor. So how many groups of 188 can we make with 628? We can make 3 groups with 64 left over. We keep going. So we can write 188 as 2 groups of 64 with a remainder of 60. And now we can write 64 as 1 group of 60 plus 4. Again, let me just draw these arrows in so we know where everything's going. All the divisors become dividends. All the remainders become divisors. Then how many groups of 4 can we make from 60? We can make 15, in fact, with a remainder of 0. So by Theorem 39.2, we know that this guy, which is the same as our final remainder, final non-zero remainder, this is the GCD. It's the GCD of 4 and 60. And by repeated applications of Theorem 38.1, well, it's the same as the GCD of 816 and 2260. So let's look at one more example. Let's show that for some natural number n, we want to show that the greatest common divisor of 3n plus 2 and 5n plus 3 is 1. And whenever you have a greatest common divisor of 1, we call these numbers coprime. So 3n plus 2 and 5n plus 3 are coprime because their greatest common divisor is 1. 9 and 8 are another example, kind of one of the easier examples of coprime numbers. They do not share a common factor other than 1. So let's use the Euclidean algorithm again. So long division will help us here. Let's do out the long division here. So I can write 5n plus 3 as some multiple of 3n plus 2 plus a remainder. So let's do some long division to figure this out. So 3n plus 2 into 5n plus 3. So 3n plus 2 goes into 5n plus 3 once. So we'll subtract 3n plus 2, and we're left with 2n plus 1. So it's one copy of 3n plus 2 plus a remainder of 2n plus 1. All right, let's do the next step then. So let's write 3n plus 2 as a multiple of 2n plus 1. In fact, it's kind of pretty easy to see. We can do it once with a remainder of n plus 1. And maybe I'll put brackets around this as well, just to indicate that they go together. So we could do long division just like we did with the previous step to figure that out. So we keep going. So we want to write 2n plus 1 as some multiple of n plus 1. Well, we can only do it once. I need brackets around that as well. And we have a remainder of n. So now we write n plus 1 as a multiple of n. And we can do that once with a remainder of 1. And hey, we need to write now n as a multiple of 1. And so n times 1 is n, and we have nothing left over. So by Theorem 39.2, we know that this is our GCD. So the GCD of 3n plus 2 and 5n plus 3 is indeed 1. And now, well, let's go back. Let's call it example 0.1 continued. Because I want to write what do I want to write? I want to write 4 as a linear combination of, what were the numbers? 816 and 2260, I believe. Yes, so a combination of 816 and 2260. So that's what we want to do. And we're going to use our work from figuring out the greatest common divisor to help us out. So let's start with the second last line. So we know that 64 equals 1 times 60 plus 4. If you remember from all the way, let me scroll back up. From all the way here, we're just going to use this information here. Can I copy this and drag it down? Maybe I'll try that. And then, oh yeah, might have to do this in a couple of stages. That's okay. All right, let's put this over here to help us out. There it is over there. Right, so we have our information here. I'm going to start at the last line with the greatest common divisor here. We're just going to rearrange for it. And the whole idea is we're going to back substitute all the way up until we get to the numbers 2260 and 816. We can now write 60 as a linear combination of 188 and 64. We just solve the equation above it for 60. So let's do that. So this is saying that 60 is 188 minus 2 times 64. So we'll substitute that in. Here's 60, here's 60. So we'll substitute that in. So we get that 4 is 64 minus 1 times 188 minus, it's getting a little messy. Bear with me, sorry guys. Minus 2 times 64. I'll write the next line a little bit neater. Hopefully that's okay. And we can simplify that a little bit. So we have 64 minus 264. So we have that 4 is 3 times 64 minus 1 times 188. So we've covered our first line here, our second line. Let's go up and let's write 64 as a linear combination of 188 and 628. So we know that 64 is 628 minus 3 times 1. 88, sorry, 188. So now we substitute that in. So we'll substitute 64. Here's our 64 here. So we'll substitute that in. So we get that 4 is 3 times 628 minus 3 times 188 minus 1 times 188. We simplify. So we get that 4 is 3 times 628. And here we have 3 times negative 3 is negative 9 minus another one, so that's minus 10 times 188. And you can check this with the calculator now, that this indeed gives us 4. And we just keep going like this. Once you get one step, you know how to do it for the others. We'll move up to the next line. It's just a little bit of work of simplifying. So we'll move up to the next line. So we want to write 188 as a linear combination of 816 and 628. So let's do it. So 188 is 816 minus 1 times 628. So again, we'll substitute and simplify. So we get that 4 is 3 times 628 minus 10 times, well, what do we have here? We have 188 is 816 minus 1 times 628. So we get that 4 is, well, here we have negative 10 times negative 1 is positive 10. So we have positive 10 628s plus 3 628s. So that's 13 628s minus 10 times 816. Just cleaning up the top. So now we've written 4 as a linear combination of 628 and 816. So let's do our last line here. We're going to solve the top equation there for 628 for the remainder. So we guess that 628 equals, what did that equal? Oh, how did that go? Like this. So that was 1 times 628. Okay, so 628 is 816. Oh no, it isn't, sorry. It is 2260 minus 3. 2 times 816. Looking at our top equation here. Oh, I have these check marks in the wrong place. Can I change that easily? Yes, I can. There we are. So we're just doing a top equation there. So solving this equation for the remainder, 628 is 2260 minus 2 816s. There we go. So we'll substitute that back in. And we get that 4 is, well, here is our 628. So we will substitute that. So we get 13 times, oh, wrong color. 13 times, well, 628 is 2260 minus 2 times 816 minus 10 times 816. And we just simplify. We see how many 2260s and how many 816s we have. So we have 13 2260s, 13 times 2260. Here we have 13 times 2 is 26, so it's negative 26, minus 10 is minus 36 8/16. And when you do this, for the most part, especially if you have two positive numbers that you're taking the greatest common divisor of, you'll always end up with you having one negative integer and one positive integer for a linear combination that gives you the least common multiple. You can't say which is which, but one will be negative and one will be positive because the greatest common divisor is smaller than both of them, or at least not bigger than both of them. So you can't have them both positive or both negative. Then you'll either get something too big or too small. So that's the method there. All you're doing, again, is back substituting all of our equations here into the one above it to get a linear combination of the two original values, 2260 and 816. It's basically doing Theorem 39.1 in reverse.